So good morning, everyone. Welcome. I'm Mark Yason, and I'm from IBM X-Force, and I'm here to talk about IE's Enhanced Protected Mode Sandbox. But first, what is Enhanced Protected Mode and when is it enabled? If you are using IE in immersive mode on Windows 8 or Windows 8.1 to browse internet websites, under the hood, your browser will be running inside the EPM sandbox. It is enabled by default on immersive IE, but disabled by default on desktop IE. EPM was introduced in IE 10 on Windows 8, and it is the improved version of the Protected Mode Sandbox first introduced in IE 7. It is improved in a way that in addition to limiting write access, which helps in preventing installation of persistent malware, EPM additionally limits read access and limits certain capabilities of the sandbox process. So this talk also applies to IE 11 as well. Also, a detailed white paper is available, I think, in your Black Hat CD, and an updated version will be uploaded in the Black Hat website. So here's the outline of my talk. First is the discussion of the sandbox internals. Then I'll move on to sandbox limitations and weaknesses. Third part is sandbox escape, followed by a sandbox escape demonstration, and finally, the conclusion. So let's begin. Let's take a look at how the EPM sandbox works. First, I'll give an overview of the different sandbox components and discuss them in details in the succeeding slides. The IE sandbox is composed of two processes. The frame process, also called the broker process, hosts the browser window and performs the privilege operations. The tab process, also called the sandbox process, hosts the browser tabs and processes the untrusted data such as HTML and JavaScript. The broker process runs in medium integrity, while the sandbox process runs at low integrity or in a more restrictive app container if EPM is enabled. Through API hooking, the IE shim mechanism provides a compatibility layer for browser extensions to run in a low-privilege environment. For API calls that would result in the execution of a process or a COM server, IE shims looks at the elevation policies to determine whether to forward the launch-type API calls to the broker so that the broker will call the API on behalf of the sandbox process. For inter-process communication, ComIPC is used by IE shims and components in the sandbox for invoking the services exposed by COM objects in the broker. Additionally, the shared memory IPC is used by the components in the sandbox and components in the broker for inter-process messages and for sharing data. So how exactly is the tab process sandbox in EPM? In EPM, the tab process is mainly sandbox using app container. App container is a new process isolation mechanism introduced in Windows 8, and it's the same sandboxing mechanism used in Windows Store apps. You can think of app containers as boxes in where processes runs in, which limit what they can access or limit what they can do. App containers are given a set of capabilities, so processes running in them can access specific resources or perform certain capabilities. IE uses a separate container when browsing internet sites, and it also uses a separate container when browsing trusted home and corporate internet sites. The only difference is that the app container used when browsing internet sites has additional capabilities assigned that allow access to private network resources. Under the hood, in the kernel, the token structure had been modified to support app containers. App container processes are assigned with what is called a lowbox token. A lowbox token have the token lowbox flag set and the integrity level set to low. The app container where the process runs in and the capabilities assigned are also set in the Lobox token. Another important field in the Lobox token is the Lobox number entry field. It links the token to what is called an app container number or a Lobox ID. You can think of a Lobox ID as IDs assigned to app containers, and this ID is used in various isolation and restriction schemes that I will discuss later. Here's how the APM process tree looks like. So the broker process runs in medium, while the sandbox process runs inside an app container. If you look at the sandbox process, you'll see the app container seed and the capabilities assigned. What is important in our discussion is the Internet Client capability and the Internet Explorer capability. The Internet Explorer capability is the value that ends with 4096. Unfortunately, Process Explorer can't resolve some of the capabilities into their friendly names. Now that we have an overview of app containers, the next question is, what are the different restriction or isolation scheme it provides? Well, one of the important restrictions provided by app container is that in order for an app container to access secureable objects, the secureable objects such as files, registry keys, or folders, secureable object would need to have an additional access control entry specific for the app container or all application packages, which means any app container, and a capability ACE that matches one of the app container capabilities. I'll show an example of this third one in the later slides. What this means, for example, is that the app container process will not be able to access personal files, such as those stored in the documents, pictures, and videos folders, because these folders don't have an access control entry for any of these. So since access to secureable objects are limited, where does app container processes store their data? In the file system, there's an app container specific folder where processes can create files. And in the registry, there's an app container specific registry key for data storage. So on the image on the left, you can see that the app container specific folder have a full access ACE is specific to the app container. In this case, IE's app container. On the image on the right just shows an example of a folder, in this case the Windows folder, having a read ACE for all application packages. Also, browser-related data located outside the app container-specific locations can also be accessed by the Sandbox IE because they have an Internet Explorer capability ACE. An example of this are the feeds folder and the favorites folder and a few subkeys of the user-specific Internet Explorer registry key. So in this illustration, you can see that the favorites folder have a read-write ACE for the Internet Explorer capability. Another isolation scheme provided by app container is that name objects created by the app container process will now be inserted into an app container specific object namespace instead of the per session object's namespace. This mitigates name object squatting, a privilege escalation attack which relies on processes with different privileges sharing the same object namespace. Also, global atom table entries now track which app containers are referencing them. This prevents arbitrary querying of global atoms, which could result in information disclosure. This also mitigates deletion of global atoms, which could be a vector for sandbox escape. UIPI, which was introduced in Windows Vista to mitigate shadow attacks, was also updated. In Windows 8, Win32k blocks write-type messages across app container. This is done by comparing app container numbers if the integrity level of the processors are equal. And finally, network access requires certain capabilities. By default, when visiting internet and public network sites, IE's app container only has the internet client capability. This means that access to trusted home and corporate networks are blocked. Now that we know some of the app container restrictions, let's now look at the well-known restrictions or isolation scheme not applied by APM. Restricted token, which could further restrict access to secureable objects, is not applied. Job object restrictions, which can prevent access to the clipboard and other resources, are not applied. And finally, desktop and Windows Station isolation is also not implemented. Without these restrictions in place, some forms of information disclosure attacks are still possible. I'll discuss them later in the Sandbox limitations and weaknesses section. As you can see in the illustration, the job object assigned to the Sandbox process doesn't have any strict restrictions in place, while there are open handles to the default desktop and the default Windows Station. So that's Sandbox restrictions. Let us now take a look at the different Sandbox components. The first component is IE shims. IE shims is used as a compatibility layer for extensions to run on a low privilege environment. In the Sandbox process, it intercepts API calls and it either rewrites it to a writable location so that the API call will succeed, or it will be forwarded to the broker process so that the broker process will perform the API call on behalf of the Sandbox process. For launch-type APIs such as WinExec or Create process, IE shims first consult the elevation policies to determine whether to forward those launch-type APIs to the broker. To illustrate, certain API calls are intercepted in the Sandbox process. IE shims will either rewrite the resource name to a writable location so that the API call will succeed, or IE shims will forward the API call to the broker, and then the broker will perform the API call on behalf of the Sandbox process. I mentioned earlier that IE shims consults the elevation policies to determine what to do if it had intercepted the launch-type APIs. Elevation policies determine whether to prevent launching of the application or a COM server. An example of policy number 0 is cmd.exe. So it doesn't when a spawning of CMD had been intercepted, the API call will just be ignored, and then or launch the process inside a Sandbox. Or policy number 2, launch the process in medium integrity but ask the user first. Or policy number 3, launch it in medium without any prompt. An example of policy 3 is Notepad. So when you try to execute the Notepad, it will be forwarded to the broker, and then Notepad will be executed in medium without any questions. So elevation policies are stored in the registry and are consulted by both the Sandbox and the broker process. So for illustration, suppose that IE shims intercepted an API call to spawn Notepad. What will happen is that IE shims will consult the elevation policies, and it will find out that Notepad should be executed in medium without prompt, so the API call will be forwarded to the broker. And this is important. The broker will recheck the API call against the elevation policies, and it will find out that yes, Notepad should be executed in medium without integrity, without prompt. So the broker will execute Notepad without any questions. Now suppose CMD is being executed. What will happen is that IE-shims will consult the elevation policies and will find out that CMD.exe should be prevented from launching. So the API call will be ignored. You might think that we can just directly forward our API to the broker. But what happens is that the broker rejects the API call, and that the broker will find out that CMD.exe shouldn't be executed. And so the broker will just ignore our call. I've talked about API calls being forwarded to the broker. Let's now take a look at the mechanisms that makes API forwarding and communication between components in the broker and the Sandbox process possible. The Sandbox and the broker process communicates using two IPC mechanisms, shared memory IPC and COM IPC. The shared memory IPC is used by the components in the broker and the Sandbox process for exchanging inter-process messages and for sharing data. 3 shared memory sections are created for communication. When the broker process starts, it creates the shared memory sections, and when the Sandbox process starts, it opens the shared memory sections. Internally, the shared memory sections are called spaces, while the data shared or communicated in these spaces are called artifacts. The broker and the Sandbox process both use messaging events so that they can be notified if a message is available for them in the shared memory sections. I was able to find out how the shared memory is structured and also able to understand some of the important fields. If you are interested on further details, you can refer to the white paper. But for a high-level explanation, each shared memory is called a space. Its space is divided into chunks of memory called containers. Each container holds specific types of data. For example, this container will contain shared data, and this container contains IPC messages. Each container is then subdivided into container entries, and each container entry contains the actual artifact, which contains the actual data being shared or communicated. COM IPC is the second IPC mechanism used. It is used by the Sandbox process to invoke the services exposed by COM objects in the broker. It is bootstrapped by the broker by first marshalling this particular interface of this particular user broker object. Once the interface is marshaled, it will be transferred to the Sandbox process via the shared memory IPC. So I have an illustration. So the first IPC mechanism, as I discussed, is the shared memory IPC. It is used by components in the broker and the Sandbox process for exchanging inter-process messages and for sharing data. The COM IPC mechanism, on the other hand, it is bootstrapped by the broker by first marshalling an interface of this user broker object. The marshaled interface is then transferred to the Sandbox via the shared memory IPC, and then it will be unmarshaled in the Sandbox process. And then once it is marshaled, IE-shims and components in the broker process, in the Sandbox process, can then use it to invoke the services exposed by COM objects in the broker. So the final component I'll discuss are the services exposed by the broker process. I use the term service for any code running in the context of the broker that are reachable or callable to the Sandbox process via the IPC mechanisms I discussed. These are codes that needs to perform privileged operations or operations that need to run in the context of the broker process. The first set of services are the services exposed by the user broker COM object. It is mostly consists of services for launching elevated process or COM servers. An example is the WinExec service exposed by the user broker object via the IE user broker interface. I mentioned earlier that IE shims forward launch type API calls to the broker. IE shims call this particular service when forwarding WinExec to the broker. Additionally, the user broker object is used to instantiate other COM objects in the broker. These other COM objects are known as known broker objects. They can be instantiated by calling the create known broker object of the user broker object that I previously discussed. Known broker objects are a collection of COM classes, each COM class exposing one or more interface and each interface exposing one or more services. Known broker objects provides additional and miscellaneous services that are callable to the Sandbox process. An example of this is the API call that handles the forwarded create file WAPI or displaying the internet options dialog box. So is the illustration of the user broker object and the known broker objects. The user broker object exposes services that is mostly used to run elevated processes or COM servers. It is also used to instantiate the known broker objects. Known broker objects, on the other hand, exposes additional and miscellaneous services to the Sandbox code. And the services exposed by these COM objects are callable via the COM IPC. Finally, the third set of services that I'll discuss are the services that are exposed by the broker components. These broker components exposes message handlers that are callable by the Sandbox process through the shared memory IPC. An example of these components are the browser frame component in the broker. It has multiple handle functions that handles the inter-process messages. Also, the download manager component in the broker have a download message function that handles IPC messages that coming from the shared memory IPC. These message handlers typically call ISO-get-message buffer address to retrieve the IPC message that was sent to it via the shared memory IPC. To illustrate, components in the broker have message handlers that can be invoked by the shared memory IPC. And at last, I finished discussing all the different Sandbox mechanisms. And this is how all the pieces fit together. To summarize, the broker process runs in medium, while the Sandbox process runs at low integrity or inside an app container if EPM is enabled. Through API hooking, the IE-shims mechanism provide compatibility layer for browser extensions to run in a low privilege environment. Also, IE-shims consult the elevation policies to determine whether to forward the launch type APIs to the broker. COM IPC is used by components in the Sandbox and IE-shims for invoking the services exposed by COM objects in the broker. And shared memory IPC is used by components in the broker and the Sandbox process for inter-process message exchange and for sharing data. Let's now take a look at the EPM sandbox limitations and weaknesses. Earlier, I talked about the different isolations and restriction schemes applied by app container to the sandbox process. I also discussed that some well-known restrictions or isolation schemes, such as job objects, restricted tokens, are not being applied by EPM. So with all that information in mind, one important question that needs to be asked is that, is there anything that code running in the sandbox can still access or do? Well, it turns out that there are still resources that can be accessed and attacks that can be conducted. So in the file system, the sandbox process can still list and read most files from system and common folders because they have a read access ACE for all application packages. The reason for the all application packages ACE in system and common resources is for compatibility with app container sandbox applications. Because if you think about it, applications need access to certain resources, such as system DLLs, configuration in the register keys, in order to properly launch or operate. But the implication, of course, is that installed applications can be listed, and the resulting information can be used for future attacks. License key files or configuration files, which may contain sensitive information, can also be stolen if they are stored in the system or common folders. There are also a few user-specific folders, those under the user profile folder, that can also be accessed because they have the all application packages ACE or the Internet Explorer capability ACE. An example of this, as I discussed before, is the favorites folders. But more importantly, EPM cache files and EPM cookies, which contains potentially sensitive information or information for authentication or website authentication information, or may contain personal information, can also be stolen because they are stored inside the app container specific folder in which the app container process has full access to. In the registry, most system and common keys can also be read because of the all application packages ACE. Again, the reason for the all application packages ACE is for compatibility with app container sandbox applications. This means that the sandbox code can retrieve system configuration information which can be used for future attacks. For example, a code can enumerate the elevation policies and find out what are the registered applications that can be run in medium without prompt and possibly attack that. Also, some form of personal information are still readable, such as those under the Windows NT current version key. And more importantly, several user-specific keys, those under HKCU, are also accessible because either they have the all application packages ACE or the Internet Explorer ACE. Example of this register keys, which contains potentially sensitive or personal information, are the recently run commands, names of recently opened files, and type URLs in IE. EPM could potentially lock down access to user-specific locations, such as in the HKCU or the user profile folder. However, that would mean that the broker process would need to do a lot of heavy lifting, because if that is the case, a lot of access requests will need to be forwarded to the broker. For clipboard access, the sandbox process can also read from and write to the clipboard, because there's no clipboard restrictions. There's no clipboard restrictions in the job object assigned to the sandbox process. In addition, Windows Station Isolation is not implemented, which means that the Sandbox process shares the clipboard with other processes running. Interestingly, a caveat I found is that the app container process should be the process that is currently actively receiving keyboard input in order to access the clipboard. So a little social engineering which will coerce the user to press a key while a window or a control is shown by the Sandbox process is needed to go around the restriction. Nonetheless, clipboard access is still possible and may result in the disclosure of potentially sensitive information. For example, if you are using a weak password manager that doesn't regularly clears the clipboard. Clipboard write access can also be a vector for Sandbox escape if applications fully trust the content of the clipboard. Also, because UIPI does not block read-type window messages such as wm-get-text, and that the UI limit handles restrictions is not set in the job object, and that desktop isolation is not implemented, screen scraping attack, which can be used to capture potentially sensitive information from windows or controls by other processes, is still possible. Similarly, performing a screen capture is also possible. And finally, because of the internet client capability, the Sandbox process can still communicate and send stolen information to a remote attacker. The internet client capability can also be used to make the affected system a proxy to attack other systems. So in summary, some types of potentially sensitive or personal information can still be stolen, either because how the access control list of those files, folders, registry keys are set up, and because the EPM did not apply some of the well-known isolation or restriction schemes. So let's now take a look at the potential vectors for Sandbox escape. Common to all Sandbox implementation is using a kernel boot bug for escape. In this particular vector, the attacker is not really interested in the Sandbox mechanisms, since the attacker will be directly targeting the operating system. And as more and more widely deployed software adopt sandboxing technologies, we can expect that kernel boot bugs will continue to be more and more valuable. An example of a kernel boot bug used to escape the browser sandbox is when John Butler and Niels used the Winter2K bug to escape the Chrome sandbox in Pwned 2013. So just to illustrate, an attacker is really not interested in the sandbox mechanisms, since the attacker will be directly targeting the operating system. So next escape vector is policy or permission vulnerabilities. This involves weaknesses in the sandbox policies, such as write aloud sandbox policies, or in the case of IE, permissive elevation policies. This also involves looking at the access control entries of files, registry keys, and finding what are those that can be written to. When I audited IE, this is actually the first vector that I looked at, because auditing for this is pretty straightforward. You just need to list all the elevation policies that allows launching in medium without prompt, and then determining whether you can control that application to run your own code. For example, via command line switches. So I did the elevation policy audit, and I think it took me a day or two. And I unfortunately found nothing. However, evidently, A few months after, Fermin Serna, another security researcher, did found and documented a policy vulnerability in IE. So the lesson I learned here is that I need to do multiple sweeps and keep digging because I might have missed on the first sweep. So to illustrate, policy or permission vulnerabilities involves permissive sandbox policies, which in the case of IE, permissive elevation policies. This also includes looking for resources in which the sandbox process has still right access to. If those resources are being read by higher privilege process, then that might be an opportunity for sandbox escape. So my first audit was a failure. So the next question in my mind was, is there a way to fold the policy checking instead? Policy check vulnerabilities involves weaknesses in how resource names or command lines are evaluated against the sandbox policies. Maybe you can cause the policy checking to return an incorrect result. So via static analysis, I looked at the code that performs the policy checks, plus any supporting code, such as code that parses the command lines, the resource names, that are used as supporting code for the policy checks. And this time I got lucky. I found a bug that allowed me to launch an executable in Medium without any prompt. The bug was in a command line parser, which result is eventually used in an elevation policy check. And that is not all. The bug was very easy to exploit. You just need to use a tab instead of a space for delimiting an application name and arguments. So in this particular case, the broker will think that I will be executing Notepad. But when the broker passed this to WinExec, WinExec will execute cmd.exe instead. So you can just imagine what a simple tab character can do. So this is the bug that I will use in my sandbox escape demonstration later. So to illustrate, policy check vulnerabilities involves weaknesses that will cause the policy checks to return an incorrect result. There are no problems with the elevation policies. It is how resource names or commands are evaluated against those elevation policies is where the weaknesses are. And finally, the services exposed by higher privilege process are a large attack surface for sandbox escape. Earlier, I had discussed the different services exposed by the by the IE broker process. Those services runs in the privileged broker context and uses untrusted data as input and are reachable by the COM IPC or the shared memory IPC. An example of a service vulnerability is the bug in the reader sandbox that was used by the first in-the-wild reader sandbox escape exploit. In that particular case, a broker service passed an incorrect output buffer size to an API, which in turn led to a buffer overflow. The buffer overflow contents can be controlled by the sandbox process, so the sandbox process was able to control the execution flow of the broker process. So to illustrate, service vulnerabilities involves weaknesses in the service exposed by the higher privilege process. In the case of IE, this includes services exposed by the user broker object, the non-broker objects, and the message handlers exposed by components in the broker. We can expect that additional services will be added to support new browser features and functionalities. So to summarize, escape involves taking advantage of weaknesses in a higher privilege code. Permissive policies and permissions and incorrect handling of untrusted data are prime examples of weaknesses that can lead to sandbox escape. And weaknesses in the sandbox mechanisms themselves are also a potential vector for sandbox escape. So I'll now demonstrate a sandbox escape using the vulnerability that I previously discussed. I have two demonstrations. The first demo is against desktop IE running with EPM enabled. In that demo, the demo will show a message box so I can explain step by step of how the attack will be conducted. And the other demo is against immersive IE, in which the sandbox escape exploit will be automatic. So I will first run desktop IE with EPM enabled. As you can see, the sandbox process is running inside an app container. What I will do is before attacking the broker, you need first to inject code in the sandbox process. In my case, I will be injecting my sandbox escape exploit in the sandbox process. In a real attack, a remote exploit will typically download the sandbox escape exploit or additional payload in the app container specific folder and then inject it in the sandbox process. So in this case, the sandbox process have the PID of 3028. So the exploit code says that it is injected into the PID 3028. And as you can see here, the attack code is injected into the sandbox process. So once I click OK, it will perform the attack against the broker process. So here you go. So what happens is that the calc.exe is executed in medium integrity. And then cmd.exe was also executed in medium. As you can see, the command line is the attack string that I previously shown in the previous slides, and the application that is running is cmd.exe. So I will now perform the same attack against immersive mode IE. So as you can see here, the sandbox process is running in an app container. So then I will inject my code to the sandbox process with PID 1276. And then the exploit will be automatic, no message box will be shown. And here you go. So calculator is running in medium, and then cmd.exe is running in medium. So that is a sandbox escape using a tab character. In conclusion, because of app container, EPM certainly helps in preventing theft of personal files and corporate assets from the network. However, as discussed, there are still some types of potentially sensitive or personal information that can still be stolen. EPM can also be further improved by combining app container with other restrictions or isolation schemes such as job objects and restricted tokens, desktop and Windows Station isolation. And finally, if you're a security researcher app container is an interesting feature to further look at, because certainly there are more interesting restriction or isolation schemes it provides than what are presented here. Here are my major references. A list of complete references can be found in the white paper. Thank you for listening, and I'll be glad to answer any questions that you might have. Yeah, thank you. Is there any questions? Questions? All right, questions? Oh, yep.
I feel it's a bit strange to put if you run, let's say, a calculator, you're still running in the normal privilege mode.
Yes.
I don't understand this design. Why a sandboxed application can run something, then it can be escaped from the mode? Why not run everything, let's say calculator, also in the sandbox mode?
Because for compatibility reasons, for example, if you are running Notepad and Notepad should access resources that is not reachable if Notepad is sandbox, it cannot access some resources. So it needs to be elevated, so it can additionally access additional resources.
Yeah, but then the attacker can easily use a Notepad to edit some system configuration files.
Yeah, but if you run Notepad, I believe it will be manual. If you can run Notepad and then pass a specific command line to override, then that will be possible. But I'm not sure if you can use Notepad to do that kind of stuff. Because if you are running Notepad and the user needs to type and specifically save the file, so it needs some user interaction. So the elevation policies, you will be attacking it by listing the elevation policies and determining what applications can be run in medium without prompt, and then try to understand if you can control those applications to do what you are trying to say. For example, via command line switches. For example, you have an application that you pass an argument, and that argument will be executed by that application. So that will be a sandbox escape. Okay. Any more questions? Anyone? Okay. Thanks again, everyone.